finishing before the break with this plate commemorating this discussion between Banach and Nikodym. I will return to this later. Of course, as you can guess, it was used as a breaking point for a coffee. And now we go back to the main topic, quantum, chaos and complexity. And here I was thinking, well, let me make a short review. There are so many notions, so many attempts. You cannot review all of those. And as far as I know, several of those notions were discussed during this workshop. So I only mention that first, my observation was that this kick top described by, look, is a concrete matrix of arbitrary size J. You fix J. Now, you have J square Z. You know what is this? It's a square of the basically diagonal matrix. You know what is JY, the representation in 2J plus 1 dimensions of this operator. And this matrix is unitary. And even though it's produced by a concrete formula, so it has low cohomology complexity, the great achievement of Fritz Hacker 40 years ago and his group was to show that they check statistical properties of eigenvalues, eigenvectors, many different properties of family of such matrices, and they show that those deterministic quantum systems are well described by theory of random matrices with high cohomology of complexity. So you see, it's kind of a apparent contradiction. It's not a contradiction, but it gives us a question. So how to define complexity for quantum dynamics? Is complexity of this operator low or high? So as you can guess, my answer is simple, it depends. So it depends what the measure of complexity you will choose, it depends what properties you wish to study, and then it only shows that it's not so easy to really say, this dynamics is complex and this is not. It's more complicated, and that's that. So I will not go too much into details to discuss all those notions, but perhaps you have heard about this OTOC, out of time order correlations. You have two observables, you evolve one in time, so T is discrete 1 to 5, and you look at such an expectation value. Another form is to take the commutator of A in time T and B in time 0, and they are related somehow. So the main idea was put forward many years ago, even before Hacker, by Larkin and Ovchinnikov, but it was popularized, let's say, 10 years ago, but many papers. Then there is another notion of geometric complexity. Usually we refer to the paper of Nielsen, then he had many papers related. The idea is simple. If you have a group of unitary matrices, of course there is one important matrix distinguished. Which one? Identity. You do nothing. You stay like this and do nothing. It's identity. And all others are different kind of rotations in many-dimensional space. So his idea was, here is identity, here is U, and in a sense you can ask how far is U from identity, but the question is how to define the measure, the distance of the geodesic. So I took this figure from this paper, I will mention this paper again, but there are many different approaches, but the idea is somehow to characterize the shortest path or the reasonable distance between identity, so doing nothing, which the identity is certainly not complex. You stay like this and do nothing. And all other evolutions can be more or less complex, and in a sense this is the main idea, which is developed now for for 20 years by many different people. And then another one is this, so you perhaps heard a lot of talks about holographic, I have now second about complexity by, I put here one name, Susskind 2016, but there are many papers about it. And here I put this name of circuit complexity, which is very much used in the theory of quantum information processing. You take unitary matrix, let's say of size 2 to k, k is number of qubits, here k is 1, 2, 3, 4, 5, 6, and then you consider a set of elementary gates. And this very important theorem, which basically tells us that any gate of any size can be decomposed in gates of order 2 qubit gates, so they are matrices of size 4, and this is the so-called bricklayer structure. Of course, it needs not to be such regular. Usually, in the real algorithm, it's not as regular. But the key point is that you can mathematically show that such a decomposition is possible. So here is U of size 2 to k, and here are different matrices of size 4. And now the question is, well, two questions. So what is the length of this sequence? Sometimes we say a depth of this representation. And then second, how many gates are used? Sometimes you have no gates. So there are two somehow figure of merits you want to optimize. And you can say, this circuit will be not complex, simple, if the depth is small and the total number of elementary gates is small. Interestingly, the set of elementary gates is very small. It contains only 1 qubit gates, and a single is enough to have a C0 control NOT gate to represent any matrix. So I think, maybe you will correct me, there is one paper by Jefferson and Meyers in 17, but there were several papers, maybe even earlier. Then I'm sure you heard about crew of complexity, so how the operator grows in time. So there was one paper of Paul Zaputa with some other colleagues, I forgot with whom, but you had papers, okay, now you have many papers about it, yes? Okay, but wow. So those topics were perhaps covered. Therefore, I will now discuss other ideas I like, because there is maybe not so well known, it's not so clear that it will be the best possible choice for defining complexity, but it uses the notion of Wigner function. So usually here we had this is a picture of a Wigner function for the so-called cat state. So there's large probability here and there. So this is the phase space like P and Q. And Wigner function, you might know the definition, is a kind of Fourier transform of such a function which depends on the initial state. So here is a cat state, so superposition of two states. And you see some here interference ripples. And if you have a Gaussian state, it's everywhere positive. However, for such a cat state, you have positive part, but you have something below zero. And then you can quantify somehow, so our paper was called Negativity of the Wigner function as an indicator of non-classicality. It was written, as you see, more than 20 years ago. And we claimed that the more negative, the larger this part below, the more complex the structure of a state, of a classical simple state. And then this notion was generalized somehow or changed. This was done for infinite dimensional Hilbert space. Then there was the Wigner function defined for finite dimensional Hilbert space. And they also defined the same idea of Wigner negativity. Since Wigner function is normalized, you can take, so here it was integral. Since integral v of pq dp dq is equal to 1, you can always normalize like this. So our idea was to take absolute value v of pq dp dq and check -1. If it's everywhere positive, then -1 will be 0. But of course, for some states, if you have negative parts, then taking absolute value, this integral will be larger than 1. So subtracting 1, you will get something positive. It is kind of a sign that the state is non-classical. So later on, some colleagues told me, well, it's true that it's not easy to compute absolute value, so they changed it to some other function, but the idea is to describe to characterize the effects of those non-classical effects of negative Wigner function. And then in the very recent paper, I think it looks like Indian paper, so here is this negativity in this discrete. So instead of integral, we have sum for discrete Hilbert space, and they studied not this function per se, but to study complexity of dynamics, they study how this negativity grows in time. So they had a simple state, the operator, and they said, if this negativity is produced, then this dynamics is complex, complicated. So this is, I think, nice idea, even maybe not so useful for every purposes. But as you see, in general, if there are so many different notions to describe complexity, then one thing is certain: there is no universal definition of complexity, but for different purposes, people try to adopt and advocate different notions. So I would guess that perhaps this idea about Wigner function might be useful. Sorry, please say.
What is this quantity W? Does it have a physical?
Okay, W is just probability distribution. It is Wigner function. So, Wigner function, in a sense, is quantum probability distribution on the plane. But to match marginals, you can show marginal, you know what is this? This is the like sum over xy to have probability distribution. Wow. The interpretation is simple. This is the quasi-probability distribution, quasi because it has negative parts, and negative parts are required to produce at this axis and this axis. You want to have, okay, let me write it down. You want to have standard probability distribution, which you study in this physics course, namely P of x. It is psi of x square, and P of q. It is psi of q square. So you have representation momentum and position representation, and you want to have such a function v such that if you integrate over q, you will get this probability. If you integrate over p, you have this probability. And then it happens, if you have a Gaussian state, it's possible to create such a Wigner function which is positive everywhere. But typically, in general cases, it's not possible, and it has to be negative. And this is kind of general feature of the Wigner function. And in a sense, this negative part tells us in some sense how strange, how quantum the state is. And one more thing, if you average this Wigner function over some fraction of the phase space, you will get Husimi function or Q representation, which is everywhere positive, which is also used. I will use it in a second, so maybe I will write it down for you. So this function is called Husimi, or Q representation in quantum optics. And this H of, let's say, PQ of state rho is just coherent state. PQ will be a coherent state, rho and PQ. For pure states is nothing else as PQ is a coherent state, psi square. So in a sense, it's a projection of a given state we analyze in the basis over a complete basis of coherent states. And of course, by definition, this is always non-negative. So this will be also used in a second. Okay, thank you for the question. Are there any more questions? Well, if not, let me proceed. The second and main part of this talk will be devoted to another new nice idea. So the paper is written by Lee, Bu, Koch, Jaffe, Lloyd. This year was published, but it was written in the internet like 2 years ago. And they call the name Wasserstein complexity of quantum circuits. So let me check. Who of you is aware of this notion? Nobody? Okay, good. At least one person. So you can correct me. No, but this means that it's not very popular yet. So I made a sample of, if at this audience nobody knows, then it's not yet, maybe it will be, so well known notion, never mind. And who of you ever heard the name of Wasserstein? Not many. Well, so let me tell you something. So the idea is like this. They define some strange distance. They call it Wasserstein distance. Let me now use dW. And they say, aha, the gate is complex if it can produce a huge distances. So the complexity of U is maximum over all pure states, a distance, this Wasserstein distance, between psi and U of psi. So if you have here the states and there is this Wasserstein distance, we say the dynamics is complex if for a given state it will be pushed far away from initial point to the final. So now the question, what is this Wasserstein distance? How they had this idea? What is this all about? So, you know, perhaps there are many different distances in the space of pure and mixed quantum states, like Hilbert-Schmidt, Boole states, and others. And they have the standard distance, the following property. They are unitarily invariant, which means distance between psi and phi is the same if you transform the states by any unitary U. Why? Because unitary is isometry, is a rotation. If you have isometry, the distances by definition do not change. Standard distances. However, this is not the case for Wasserstein distance. So here is this condition that the unitarity invariance is not satisfied. Look, dw of psi and phi is not equal to the distance between transform states, which in a sense you could say, it's very bad for Wasserstein, but some other people say, no, it's very good. It's very nice property. We will use this fact, and they do use the fact that this unitarity invariance is broken. So it has some appealing properties, but from my perspective, this distance those authors use has very important practical disadvantage. As usual, for us it's important to not only to define something, but to compute something. And this notion is not easy to compute. But I will be happy and use it, of course, as an excuse to show you, to return to some other stories, and to return now to, the book is of Hacke, Quantum Signatures of Chaos, and to refer to Lyapunov exponent. So again, I'm pleased that Tomasz is here, so he told us yesterday something about quantum Lyapunov exponent. I will claim that our notion of quantum Lyapunov exponent might be better than the previous one. So classically, there are classically 2 points in the phase space, and they diverge exponentially, and we know that Lyapunov exponent is positive. And then we also know that if you have standard distances, because this distance is unitarily invariant, the Lyapunov exponent defined with respect to this standard distance would be 0, because it's just the rotation. For any rotation, the distance between points does not grow. And therefore, some time ago, in fact many years ago, 1992, this was the paper with Fritz Lyapunov exponents from quantum dynamics. So of course, the idea is very simple. We take the same formula we have. So the logarithm of change of the distance 1 over t, and the initial distance goes to 0. But we ask, maybe the definition is good, but we should change the definition of distance. We should take some other distances. So this was idea put forward already, how many? More than 30 years ago. And then in another paper, also 30 years old, how to generalize the Lyapunov exponent from quantum mechanics. We just decided to propose this idea of Monge. I will mention it, it's related to Wasserstein. Monge distance between both Q functions. So Monge distance, this is now the key point of this part of the story. This is an important notion in mathematics. It's called transport problem. But not quantum transport of the electrons and current, but transport of probability. And since all those reasonable distances between quantum states are unitarily invariant, what I already emphasized a few times, we use this counter-example, the Monge distance, and try to define the Lyapunov exponent basing on this idea. And so the papers were already also 25 years ago with my co-author Wojciech Słomczyński, and the idea is extremely simple. So we use the notion of coherent states. I mentioned them here. Here I call them somewhere here. Where were coherent states? Here. They were called PQ. So coherent state, you know what is coherent state, yes? Is the eigen state of annihilation operator, for instance. But there are many definitions of coherent states. And here I denote them by alpha. So alpha is like Gaussian packet localized somewhere in the phase space. So Husimi function, or Q function, is nothing else as the coherent state representation, which by definition, of course, is non-negative. Yes, this is just expectation value. This is a Hermitian positive matrix. It has to be non-negative. So Q function is just a probability distribution on the phase space. So the idea of Monge is extremely simple. If you know the classical Monge distance, that our quantum distance, Monge distance, in the space of quantum mixed states, is equal to the Monge distance between corresponding probability distributions, those Husimi or Q functions. So now the only point is how to understand the idea of Monge, which, as you can guess, is more than 200 years old, because Monge was was officer of Napoleon, and his duty was, he did of course mathematics, and in geometry he had those Monge projections, yes? If you study architecture, I haven't, the most difficult part is to study the projections of Monge, yes? And so he was responsible for creating and designing fortifications. So those days they had no electrical supply, and all the work had to be done manually. So the key question was how to transport a pile of sand from one point to another. So look, this is standard, let's say, flat Earth approximation. And this is now known in literature as Earth-mover distance. So you have initial pile of sand, the final, you have to do something with it, you have to shift and transform. And let's say they are normalized or like probability distributions of the shapes of sand. And you want to minimize the work, but the work not against the gravity, but against the friction. So in a sense, you take a wheelbarrow and put it loaded with sand and transfer it somewhere, and you want to minimize the total integral of what is the total path traveled by the wheelbarrows you did to change one shape into another. So look, I decided to make an experiment, or I will spoil, I'm sorry, one piece of sugar. So here is sugar, and this is the initial, let's say, position of sugar or soil. And let's imagine this is the final. So I have many different, it's called mange plan. I put this sugar somewhere here or there, and I can do it in many different ways. But now I wish to find the optimal way to minimize the total transport which was done to change the initial distribution to final. Is it clear to all of you? I hope you will excuse spoiling of one Warsaw piece of sugar. And I can only tell you I'm not doing it first time, so I spoiled many such sachets already. Okay, but sometimes I use sugar, so it's better. And now, look, it's a well-defined mathematical problem, so we have some mathematicians around. So really for 200 years, some people do hard mathematics and study this problem. Even you can get, so Villani got Fields Medal for transport problem, almost. Okay, but Villani first is an important French mathematician, and he wrote 2 important books about transport problem, and he also got Fields Medal. This is true, yes? All those facts are true. Aha, okay. And he became a politician, yes, recently. So, in 2 dimensions, it's a bit complicated because look, I can take this piece of sugar and put it here or put it there, and it's not well defined where to shift. However, let me now change a little bit the problem. If I have everything one-dimensional, so here's one distribution, and I can only shift in one direction, everything is simple. I only have shift from initial, so let's assume we have here one probability distribution, Q1, second probability distribution, Q2. So basically you have to shift it in this direction as far as it's necessary to transform this distribution into this. And then, well, it took some 100 years as some Italian guy, Salvemini, wrote such a nice paper, Sul calcolo degli indici di concordanza in 1943 during the World War. And he found the first example of explicit solution of the problem. And the problem is very nice, the solution is very simple. So for any 2 one-dimensional probability distributions, Q1, Q2, you compute cumulative distribution function, po polsku dystrybuanta, F1 and F2, and you compute the integrated difference between 2 probability cumulative distribution function, which is just the area of this field between cumulative distribution function. And this is a distance. Moreover, if you have one distribution here, Q1, and second distribution here, Q2, of the same shape, then cumulative distribution function, here it will look like this, here it will look like this, because the shape is the same. So now let's see that the area between is just equal to the distance, d, this is the same distance, between the points where those 2 packets are concentrated. So in this sense, this Morse distance has such a property that if you have Dirac delta here and there, then this Morse distance is just equal to the distance between the points those distributions are concentrated. This is simple in 1 dimension. But in 2 dimension or more dimension, it's more complicated. And the most important result for us was that if you take now coherent states, they have the same shape. So one Gaussian packet here at alpha, second Gaussian packet here at beta. So the Morse distance by construction is just the length of the vector translation vector. Why? Because this is the optimal Monge plan. You don't need to think. You put this part into this part, this part into this part. You just shift entire distribution by the same vector. And then, okay, in our first papers, we computed some distances between some states known in quantum optics and obtained interesting thing that if you have orthogonal states, if they are orthogonal, so standard distances between any orthogonal state is maximal. Yes, are you with me? Because Hilbert-Schmidt distance between any two orthogonal distances is always maximal, independently whether this Fock states, let's say the number is 0, 1 or 1 in 100. So in the case of Monge, distance is not the case, and it's much closer from 0 to 1 than from 1 to 100. And this is somehow a semi-classical property. And we can also compute it for thermal states, but this is somehow not important here. Here's again the picture of Wawel Castle in Krakow from different perspective. Yes, by the way, I was told I was not today in Vistula, in Warsaw at the Vistula River, but you also have problems, there is no water in Vistula? Yes. Is there still a water or not enough? Yeah. In Krakow, so now I realize this picture is still a lot of water. Now we also have everywhere problems. Okay, there's still water, but not enough. And now I will refer to the problem of Kantorowicz. So now we use the name Monge-Kantorowicz distance. But here the point was that there is this transformation which starts with one initial state and finishes with final. So apparently there is asymmetry between beginning and end. And therefore this problem is not clear that the distance satisfies this symmetry, that this, under this definition of Monge, going back from beta to alpha will be the same. And the Kantorowicz did somehow a nice generalization, but Kantorowicz defined this transport problem in a much more general setup. So this is now a transport plan in the setup of Kantorowicz. By the way, it was done just before the Second World War, and then for him the motivation was very nice: optimal organization and planning. Why this is related to planning? Yes? No, you don't. It's okay, sorry. But you only care about the work, but where against the friction, which is measured. Okay, so I think I forgot to write it down. Let me do it somewhere here. Okay. So you take a set of transformation T, such that in general they transform Q1 of X, it could be a vector, into Q2. So there are all those Monge plans which send the initial pile of sugar into the final, and I want to minimize over all T integral Q1 of X, and now I have T of X. So T will be the vector, so maybe absolute value, dx. Because I want to say, this is the initial distribution, and I measure what is this will be the, okay, here is the T is the transformation. So here is the length of the vector of transformation which changes. And this is this Monge formulation which is not symmetric. But of course, it produces a distance which is symmetric, but in a sense this one mathematical somehow deficiency is that this is not symmetric, but it happens you can to prove that it will be the same as minimum over T, okay, let's say this set is different now, over Q2 X T prime of X dx. Prime because the set is different. Yes, the set of reverse going backwards. Yes, is it clear? Thank you. So Monge did it in a more general way, and as I mentioned, it is related, so here the motivation was planning and organization. How do you think how it is related? This transport problem has very nice interpretation. First, from concerning economy. It's used, let's say, now indeed, for the large companies which have, let's say, they produce some articles here and have customers and want to really transport goods. Moreover, which is a sad story, but it was true, that was really another motivation was war and fighting brigades, and they had munition and they want to supply in the optimal way. But also for the more peaceful applications, there is very much related to so-called allocation problem. If you have a dean who has, let's say, 10 professors and 7 tasks, and has to assign professors to a given task, it's in a sense the same problem. You have to allocate goods and to optimize some function. So this, in a sense, this Monge idea is just the same, and therefore it's so popular in different fields, subfields of mathematics, but also in economy. So I don't think I have enough time. It's not so interesting to go too much into detail. But here the main achievement of Kantorowicz was to find, Anna was again, that he has now a measure on Cartesian product, and to make everything symmetric, now he has a cost function which depends of xy, and now look, this formula is kind of generalization of this formula here, in a sense. So I want to have now transformations which transform one measure into second measure, and this is down, and it will be by construction symmetric. So now look, this cost function C, which basically the interpretation is simple, like distance from point X to Y, classical distance or cost of transport, and we want to, so the idea is, as usual, economically, you want to minimize the cost. Wasserstein did only one thing. You know what is LP distance, of course. So here it is like P parameter, P is arbitrary. So you can put this cost to power P, take integral, and take at the very end 1 over P. So from my perspective, it's not such a great achievement. So I prefer to call it Monge-Kantorowicz-Wasserstein problem. But now people, for shortage, they use only Wasserstein name. But the idea of Wasserstein is, in fact, a small modification or generalization of Kantorowicz, which is a generalization of Monge. So P is arbitrary, and as you can guess, P equal 2 is kind of distinguished. So for several cases, it's good to have here a square and have P equal to 2, but sometimes people choose, let's say, P equal 1. But the idea is relatively simple, a generalization of the standard classical problem. So this expression is just the cost, and you want to minimize it overall. So this gamma will correspond to my set T. Gamma will be set of all transformations which transform measure mu into nu. I will show a better picture in a second. Anyway, this was done classically for a set of n points in some set x which was equal to y. We had two probability distributions, like discrete probability distributions, and we want to find the distance between those probability distributions. So in the more general setup, we ask a question: what is the distance, Monge distance, between first classical probability distributions and later quantum states, or quantum probability distributions? And then, okay, we define those coupling matrices. So this is a matter of choice, but this coupling matrix usually is determined by the problem, like this cost of sending material from one place to another, which could be just a function of the distance, classical distance in the space. So here is the final formula. This is just done it's classical formula, but it's already done to prepare it for quantum. So here, rho AB will be just a diagonal matrix. C is this classical cost function, and we want to minimize over all those coupling matrices. This is a set of coupling matrices which produce probability A and B, and in a sense, this corresponds to optimal Monge plan. This is like more modern approach to the problem. And here is, again, the visualization. So first, let's assume we have a discrete probability distributions. So we look for such a probability distribution, P of xy, such that both marginal agree. So here is first distribution, PA, here is second. By the way, it's related to your question concerning Wigner. So a Wigner function is exactly such a function which gives you marginals given by wave function, and unfortunately, it cannot be everywhere positive. Here we assume that this P of x is positive, and we wish to find all those probabilities which have marginals given. This is the state of classical probability distribution in the simplex, and this is the larger set of bipartite simplex, and this is the set of quantum states. So this is state of size n, another set of size n. This is the extended space of size n square, and here we have all those states such that marginals are given. And we'll perform optimization over this set. And then, in a sense, this idea and the formula is the same. So we have to perform optimization of such a trace over all those states such that marginals are fixed. And this is easy to define, but not easy to compute. So here is a brief history of this quantum transport problem. So, of course, I started with our papers, which are 30 years old, but now there are many people which for the last 10 years work on this subject very much. One paper here is in red because in this paper from 2021, they were defining exactly this variant of the Wasserstein distance, which was used for this Wasserstein complexity. Therefore, for me, this is important. Only I will mention we had one paper which we managed somehow to popularize this in physics community. So with Shmuel, Michał, and another guy from US, Cole, we managed to publish a paper about these issues in PRL. So now, again, going to quantum and a more constructive mathematical definition, which is not so complicated. So we have two states. The idea is simple. We have two states we want to find their distance, their Wasserstein distance. So we consider a set of coupling matrices or quantum transport plans. They are such bipartite states such that one partial trace is rho A and second is rho B. So now look, in principle it's very simple. But what is not simple? To describe such a set and to optimize over it. Then, so gamma is the set of all those coupling matrices. We need a cost function, which is a Hermitian and satisfies some certain properties. And our setup is simple. The quantum optimal transport problem, or quantum Monge-Kantorowicz-Wasserstein distance, is minimum over all possible coupling matrices of this quantity trace C rho AB. As simple as that. So for given A, rho B, you look for this set of couplings and you minimize over this set this quantity. Of course, the point is how to select a suitable cost matrix C. Okay, so this is important, so I will give you a chance to ask a question. Is it clear enough? Interestingly, this problem has many applications. It's interesting also for mathematicians, but now, as you have seen, many people from physical background try to apply it for many different applications. And now I will mention this. I'm discussing this paper where they try to make use of it to describe complexity, and as usual, it's nice definition, but often difficult to compute. So here there are some now guesses how to motivate this cost function. So classically, cost function is simple. We have, let's say, 3 points, and we measure distances between them. Now you have to introduce to quantum theory some reasonable cost function and have to motivate it to convince the readers that this is a good one. So there are many papers I need to quote. One of the group of Lloyd in the US, De Palma is from Italy. Well, there is also a strong French group, so many people worldwide were interested in this. And now, classically, if you have this classical matrix of distances, it represents a diagonal matrix. So our idea will be, we call it coherification, to find this cost matrix, which will be a potentially pure state. So the one answer is this projection onto asymmetric subspace singlet state. We're very pleased with this idea, but as usual, it's occurred that we're not the first, so some other people did it here. So there is one paper from 2018, and some Chinese groups did it also earlier. So the point is that this projection onto the singlet state, you can also define but one minus swap gate. So a swap is just exchange. Now here I'm talking about one qubit system. It has this property that if you take diagonal, it corresponds exactly to the standard classical cost function. Okay, and you can take this Wasserstein idea to have different P here. As usual, you have traced this quantum mechanically. C you raise to power P, take minimum, and then take 1 over P. So the idea here is simple. In principle, you can define such a thing right away. What is more difficult is to show for which values of P and which values of the cost function you get really a distance. It's symmetric, this is easy to show. But what's not easy is to show that it satisfies the triangle inequality. Distance is always a triangle inequality. and this is not simple. So I will not bore you with too many details. Okay, I will just mention that it's related to other distance like fidelity, Bour's distance, infidelity, but I don't think I have time. It's not so important for us. Sorry for this. And we were able to find a solution to show that such a distance, it's really a distance, but only for qubits, but for mixed states. It was not so simple. And then the geodesics inside Bloch-Bohr look in a strange way. They are not, I was thinking it will be a part of a fraction of the circles, but they are not. They have such a strange shape. So here are different points, and these color lines correspond to, let's say, geodesic shortest path. It's very strange. And this is from our paper from 2022. And there are some approximations, but fidelity is such a quantity which it's like more or less for pure states, it's just like overlap, square overlap between two states. Okay, so decoherence means I want now to go from quantum transport to classical to see how it goes, but this is maybe not so important for us. It's more interesting to discuss now the following thing. The Morse distance can be well defined, but there is a hard optimization problem. And usually nobody knows, even in classical case, for two-dimensional system, how to solve analytically Morse problem. It can be done in numerical way, more or less efficient, but it's not simple. But for pure states, it's much easier. Why? Well, of course we like to work with pure states, but who knows, okay, it's difficult. Why for pure states everything is much simpler? Okay, I will tell you in a second, but I will go back to this picture. The key picture is this one. So we have to optimize over this set. This is the set of all states such that the partial traces are fixed. But look, if this is pure state, or this is pure state, then this set is only one point. Then there is only one state which satisfies, is a tensor product. So then the minimization is trivial. If you have optimization over the set which consists one point, we can do it analytically. Of course, it's a kind of a trick because then there's no optimization. But at least with this approach, we can generate analytical a nice distance which has at least some good properties. So therefore, I will skip to discussing, I think two notions and we are done. One notion is, we decided to call it energy distance. Look, let's take any Hamiltonian. Let's take eigenvalues, eigenvectors. So this will be eigenvector index j and I. We have eigenvalues. For instance, if you have a harmonic oscillator or maybe hydrogen atom, okay, let's plot harmonic oscillator because it's easier. And you know, of course, here will be like E0, E1, E2, E3, and so on. So here is state 0, 1, 2, 3, and possibly 4. And what is the distance d between state I and j? If you have standard distance, so of course this is equal to constant if for I not equal to j, and distance from 0 to 1 is the same as from 0 to 3 or to 4 or to 100. So the standard distance does not take into account fact that higher excited states are already far away from the zero state only because state I, j are equal to delta ij. So if their I is not equal to j, it's 0. And here, this approach, if we choose Hamiltonian, we can impose such a cost function that by construction, for any eigenstates of the system, their distance is equal to the difference of the energies. So the difference between, if this is, let's say, one photon, here is another photon, here is another photon, will have this property that our Wasserstein distance between state I or j and I will be just equal absolute value of I minus j, which is just counts number of photons, resonant photons, which have to be absorbed. Which is relatively simple, and it looks like nobody ever thought about it. Even though it's like natural from this perspective, it's like difference of energy. How much energy you have to pump, provided you only can use one photon, also many photon transitions, but photons are resonant. So this is the main, in a sense, assumption, which is imposed by choosing a given Hamiltonian, and any Hamiltonian defines such a distance. And now we have this property that indeed this version of Wasserstein distance with this cost function has this property that distance from 0 to 1 is much smaller than, let's say, between 1 and 100, which describes the difference of energy. And okay, so this is exactly this picture, that in the case of classical, like trace distance, all three states, they form equilateral triangle. The distance is the same. Why, in sense of our energy distance, they form Wasserstein distance, they form the metric line. So they are at the line because energy from 1 to 3, the difference is equal to the sum of energy differences from 1 to 2 and 2 to 3. So this is one application to find such a distance which somehow reflects the energy in the system. So in a sense, it's the Wasserstein distance induced by a given Hamiltonian. And here is yet another application. If you have now angular momentum operator, so you have the famous formula like Pythagorean theorem for three components, and you can take for H, let's say, this operator, and now we can use this notion to study Wasserstein distance between states and how they change in time. So in a sense, we can measure maybe not complexity, but degree of chaos. We can see how this Wasserstein distance, J, because this angular momentum is like angular momentum Wasserstein distance, between two initially coherent states, how it grows in time. And in a sense, in this way, we can return to our original notion of Monge, Lyapunov quantum, Lyapunov exponent. And here are some recent results which were obtained for this model of Fritz Hacke of quantum kick top. So K is this kick strength for K from, let's say, 0 to, sorry, this is missing the axis. Here is 1, 2, basically all those curves are almost 0. So here at this axis, you have Lyapunov exponent for different size of J. Black is the classical, and colors are different value of J, and the larger dimension. Here J is 25, so matrices are of size 50. Then this quantum version of Lyapunov Wasserstein distance, which tells us how fast this Wasserstein distance grows in time, it's closer to the classical value. So this is yet unpublished, but in the sense, so you see, Tomasz, so you were not so satisfied with the Lyapunov exponent in quantum theory. I don't claim this is the best possible, but here at least by changing the distance into this Wasserstein distance, you can observe how this Wasserstein distance grows in time, and then you can hope to describe complexity or degree of chaos for those quantum systems. Yes, sure. But please speak up. Yes, this is a good point. So of course, like a good point. So okay, in Polish we say devil is in details, because this is of course numerical estimation of the Lyapunov exponent for short times. We have no time to wait for infinity. Maybe you do, but we don't. And of course, if you wait long enough, it will be spoiled, of course. Yes. So it's of course kind of approximation, and of course there are those two important limits: time to infinity, initial distance to 0, and I agree. So therefore, I don't claim it's really the very optimal. And here, one more remark. So here now is to Radek. So please wake up. So this is now I think, to show some mathematics. Key mathematical result obtained by my colleagues Bistoy and Miller. So the idea is the following. It's a kind of quantization of the classical distance of the classical space. It's a mathematical statement. So let's assume we have now the set of n points in R to M. M is 1, 2, 3, 4, whatever. And we know distance between them. There can be any distance taken. So this matrix is symmetric. And now we want to lift this geometry to the space of quantum states. And so for any theorem says chosen classical distance, this set matrix, you can define the following Wasserstein-like distance, which is defined here explicitly for any two states with those coefficients expression in any basis. And here enter our classical distances, and the main result of Rafał and Tomasz is to show that this quantity satisfies triangle inequality and there's really a distance. So it's unpublished mathematical result. It's based on some generalized Cauchy-Schwarz inequality I have no time to discuss. Anyway, it's a strict result. And our energy distance is one part of it because it's a particular realization of this choice of the cost function. And another one is quantum Hamming distance. So what is the classical Hamming distance? If you have two strings like this one, and second is 0, 1, 1, 0, 0. So you compare them, and you see that there are a few places. Okay, here is red, yes. So where here is one, and here is second one. So the Hamming distance between, let's say, first string I and J in this case is exactly 2, because there are two flips to change, yes? So the object of looking, there are many papers on quantum Hamming distance. So the idea was to find such a distance between any states, multi-qubit states, such that for any basic states which are realized by series of strings, you have this property, and this is our definition, which is again based on the Wasserstein distance, and because of this theorem of Miller and Bistron, we can show that this explicit equation, which is, look, for any two strings, we use the classical Hamming distance to define distance between quantum states, and we can prove it's really a distance, and we hope it will be useful, well, for some optimization for random search procedure. So here is you have a time, it's a numerical procedure to look for due to random search, you want to, the goal is to go to a minimized distance to go to a given state. Let's say this will be the so-called GHZ state is a goal. And we want, the red line means we want to minimize the Bour's distance in the random search, and the blue one is minimize our quantum Hamming distance. And here is like measure of precision, here is time. So basically this curve goes down faster, so we claim if we minimize our quantum Hamming distance, we'll achieve the goal faster. So I think this is almost all. I think I should rather soon conclude. So first of all, I don't believe there is a nice unique definition of complexity, especially in the quantum domain. There are many different approaches, many different notions which can be used depending on your wish and needs. And then the key point is it's not easy to distinguish between pseudo-random sequence of numbers and really random numbers, or between quantum operators which are defined deterministically like this kick-top unitary from really random matrices from the Haar measure, because the properties are very similar. And there exist many different notions of quantum complexity, like I mentioned again, holographic, geometric, circuit, and then quantized chaotic systems. They are of a low Kolmogorov complexity because we can describe them. They produce unitary operators with statistical properties which are very, very close to properties of random matrices of high complexity. And other approaches I found recently interesting is just the evolution of this Wigner negativity, or looking for the maximal Monch-Kantorowicz-Wasserstein distance between state psi and its image. And this is important and possible only because this distance is not unitarily invariant. And I believe that this method is applicable to find at least some approximation of the quantum Lyapunov exponent. Well, we are almost done, but now I was showing you this picture of this plate in Krakow. So here is the bench in full glory. So here is Otto, Nikodym, and Stefan Banach, and this bench was opened in 2016, exactly 100 years later, after their famous discussion in Krakow. Here is a new monument of Banach, opened just last week in Ostrowsko in Podhale, close to Nowy Targ. Why there? Because this was the family place of Stefan Grecek in one of those booklets. I got it. Therefore, I was eager to show it to you because I got it last week. And you see here, it's a very famous book which was served as a habilitation thesis. So Radek, you will recognize the title? Terroir de opération linéaire It was just published in 1932, I think, yes? So there are two issues important. You know what is Banach space, yes? You do. How old is Banach space? So, well, possibly he was thinking about this in 1922, 23. But the first time the name was used, it was in the paper of Fresche, who wrote a paper and used the name Banach space, I think, in 27. So therefore, we will have 100th anniversary of this event. So I try to convince mathematicians. By the way, you are a member of the Presidium of the Mathematical Society. So I will suggest that the Polish Mathematical Society could consider organizing a conference to commemorate this fact. And the second issue is that you know the story about the PhD thesis of Banach. Maybe it's not true, but about habilitation is true. It's very nice. That he wrote this book. And he knew French from his childhood. He wrote it in French to make it accessible to Fréchet and other people. And the University of Lviv submitted to Warsaw because, of course, it was clear that Banach should deserve his habilitation thesis. But then it was refused. You know the story?
I know a different story.
Okay. And it was refused because in the Polish rule, it was written, now I have to use the Polish, because it was not the habilitation thesis was supposed to be written in język wykładowy, which means in the language of the lecture language. And they said it's written in French, so it does not satisfy the rule. But then the Council of Mathematics, philosophy in Lviv was very clever. They said, no, but they decided that Banach is supposed to lecture in French. And therefore, it will be for him the language of his lecturing. And then the rector of the University of Lviv, by the way, it was Jan Kasprowicz, a very famous person, and he wrote another letter to Warsaw, and this habilitation degree was conferred. So I learned such stories being there in Ostrowsko. And then one more remark, why is this important for physicists? We are more physicists than mathematicians. Look, the guy, second guy, so Nikodym, you know the Nikodym, what is Nikodym derivative, yes? Radon Nikodym, yes? So the same guy who was talking in 1916 with Banach, he survived the war, fortunately, and he went to US, and in 1966 he wrote a book, The Mathematical Apparatus for Quantum Theories. So he was also interested in physics. And then this book made it to the very important popular mathematical journal, it's Mathematical Intelligencer. Banach tells his side of the story. So, thank you very much. This is all what I had to say. But, yes, I think now, because I will have to go maybe not to Ostrowsko but to Krakow, I will be very, very pleased if we start the discussion now. So if you have any questions, I will be here. I will be very, very happy to discuss everything with you, whatever you wish.
So let's start with thank you. So indeed we can now, I think, have kind of extended questions and discussions. So please.
Okay, so you mentioned this a little bit in passing, but in your distance measures or complexity, you can look at kind of non-Gaussianity of states, or maybe...
Sorry, but now you refer to this idea of Wigner function?
Yeah, Wigner or this Wasserstein.
No, but sorry, but Wigner has something to do with not Gaussianity. Wasserstein, not quite. Okay, in some sense, yes. But basically, in a sense, it is related to the property how fast or how strong the Gaussian hood of a state is destroyed during the evolution. But of course, it's not only this, it's also how fast, if you start with the coherent state, wave packet, and evolve it in time, something will happen. It will be moved, but also distorted. So in a sense, this complexity should take into account two things. One, how far it goes apart, and second, how much it is distorted. And then this Wasserstein distance is able somehow to cope with both.
My question was like whether you have any ideas like how to, for example, use these tools to be used to like quantify magic.
Well, good question. So my simple short answer is I don't know. Okay, but it may happen that it is somehow already included, but no, I was not thinking about it. So, okay, no, but it's a good point because this, magic is somehow a property that the state it does not belong to some certain class of states like stabilizer states and so on. It's not related, cannot be obtained by Clifford operations. No. So I've never, very nice point, I've never thought whether how much this idea of Wigner or Wasserstein is able to realize this. No, good point. I don't know. Thanks a lot for the question.
In your presentation, you focus on Lyapunov exponent on distance,
yes.
But in classical ergodic theory, it looks completely different. It's about dynamic system, mixing, ergodicity, and so on. So why you haven't even mentioned anything like this, which are central in the classical?
Well, I'm not sure I have not mentioned. I do not fully agree. It is very different. Look, I mentioned the name of Pessin and Pessin theorem, which tells you about the relation between Lyapunov exponent and Kolmogorov-Sinai entropy, and Kolmogorov-Sinai entropy is just dynamical entropy, which is a production of entropy during the evolution of the time. So it's exactly related to producing of entropy, is exactly related somehow to the ergodicity. So of course it is related, you are right, it is related, it's closely related, but this Pessin theorem, of course, holds in the classical setup. And now for many years people tried to, first, generalize Lyapunov exponent from classical to quantum, generalize dynamical entropy of Kolmogorov and Sinai from classical to quantum, and try to find a relation between them to look for a kind of quantum analog of the Pessin theorem. And as far as I know, it's still not done well enough. So this is still something to work on. But I agree, this is very much related.
May I ask something?
Yes, sure, please do.
The Kolmogorov entropy is not only, it's only K, it's the highest chaotic property. There is also
weaker
mixing of
yes,
the lower
yes,
order,
yes.
and there may be,
Yeah, you're right, of course. So mixing is a weaker property. You don't require positive Lyapunov exponent to have mixing, sure.
But
Look, yeah, this is true. But look, my point is that it's very difficult to find a single tool which will be applicable for everything. If you have a multi-tool device, it's not as good as specialized device to different purposes. So,
I understand, but I mean the following: the K mixing is very, very high, is the strongest property. But even if the mixing is of lower order, you still have kind of chaotization, right? You have
but to have really chaos, you require positive Lyapunov exponent or positive Kolmogorov-Sinai entropy. Well, okay, at least there is some school of reasoning which says that this is kind of a simplest possible definition of classical chaos. But I agree there are many different, look, there's also this notion of Guggenheimer of sensitive dependence of initial conditions, which is weaker than chaos, because chaos means that every time during entire evolution we have exponential divergence, and then there is this weaker property that there is sensitive dependence on initial condition, but you don't require the Lyapunov exponent can be zero. So of course in mathematics, and there are those called Anosov systems. Yes? So there are many different degrees of to characterize the degree of chaos in classical systems. And it's not possible to say which is better, so in quantum it's even more complicated. Because not all of those quantities have the well-defined analogs. Thank you.
So a couple of questions. First is Wasserstein distance some sort of generality of trace distances, or how are they related?
So sorry, generalization of what?
Trace distances like fidelity and...
Okay, but they are, sorry. I would not call it the generalization. It's an alternative approach. Okay, you can bound it. So what I was mentioning that there's a very different approach, but in some cases, so look, this idea of Monge-Cantor, which is very general, but it's not unique in the sense that you require this cost function, which corresponds classically to the problem if you have, let's say, initial points of the papers and the final, let's say it's this one, and it depends on the geometry, yes?
Right.
So it's defined modulo well-specified cost function. So my point was that under different choices of cost function, you can have this or that properties, and then in some cases you can have some bounds with known distances like Buress or fidelity, infidelity, and so on. However, those classical distances like trace or Buress, they are always unitarily invariant. And our Wasserstein is not, which can be considered as a disadvantage or advantage, depending on your needs. Okay, is it fine?
Yeah, and the second one is, so if it's an alternative approach, does it also have like a are you familiar with Discord? Quantum Discord?
Yeah, sure, but...
Yeah, so does it also have like a quantum Discord?
No, but Discord is not a... wait, but Discord will not be a distance. Okay, of course, yeah, okay. Discord is defined, in a sense, by distance to some given set, which is non-convex. Okay, but... No, but Discord is a quantity which characterizes correlation in a bipartite state, but it does not explicitly allow you to define distance between any two states, yes? Discord is nothing else as a distance of a given bipartite state to the closest state which has such and such properties, yes?
Classical thought. So like
Yeah, but we discuss quantum states. We discuss the set of quantum states, and we discuss bipartite states, and we have the set of entangled states, separable, and those with zero discord, yes? With zero discord are those which are, okay, you can call them classical if you wish, yes?
Right.
Yeah, but they are quantum states with some classical properties. Yes? That they have, let's say, for instance, separable eigenstates. So this is some class, okay, sorry. Here it is. So, no, it's fine. You have a state set of all states. So I will call it omega n squared because I have n times n system. Now here I will have a set of, let's put it like this. A separable state which touches, this is separable, and entanglement can be defined, here is E of rho, here is state rho, as a measure of a distance, well-defined distance, from the state rho to the set of separable states, and for instance the state psi plus, the singlet state, maximally entangled Bell state, is as far as possible from the set of separable states. But, yes, you agree, yes? And then there are separable states, and there are also states which are of zero discord, and this set is complicated, it's more, it's not convex, and this discord is similar, but it's a difference not to this state, but to another set, yes, of zero discord states. Okay, no, so there is some relation to distance. Okay, you can also, by the way, there was also today, during the first talk, there was mentioned this idea of relative entropy of Kullback-Leibler. So the quantum version is called omega key entropy. So you can use this relative entropy as another measure of distance, and then you can have another measure of quantum entanglement by using this relative entropy of a given state to the closest, in this sense, separable state. But again, look, this omega key entropy, of course, it's not a distance, it's not symmetric, yes? It's a, this is the quantum version of the relative Kullback-Leibler entropy, yes? Okay.
One last question.
Yes?
Are there any counterexamples to BGS conjecture and Bell double conjecture? Is it possible to...
No, sorry. I could not hear acoustically. Counterexamples to what?
The Bohigas-Brioni and Schmidt conjecture?
Yes.
Is it possible to construct a quantum system which has spectra which will be randomly...
Okay, very good point. Yeah, I see now. In some sense, okay, in German the answer is Jein, which means yes and no, because it's not a mathematical theorem. To have a theorem, you have to ask mathematician. You need a firm assumptions and a thesis. And here it is not well defined. So you can construct with, in a sense, bad will, some pathological systems for which So in principle, I recall, there are some counterexamples, but in a sense, it's not counterexample to the conjecture, because conjecture is more like about typical properties. And look, one example, counterexample, which was very known and discussed, I can produce offhand right away, which is a bit trivial, but very much not so. Here is harmonic oscillator. So the spectrum, how you look at the spectrum, you have here the spectrum, yes? And of course the spacing, okay, here is very strange because spacing is what is constant. So the spacing distribution is very strange because spacing distribution in this case here is S. S is like EI minus EJ. So probability of spacing is rescaled by the average will be here Dirac delta for harmonic oscillator, which of course is not a Poissonian distribution, even though this is a regular system, yes? Okay, so this is known. But now, this was an important paper written maybe 20 years ago, the following. They did the following. They a little bit perturbed, okay, I cannot plot it like this, but they had a potential. So here is, again, here is V of X, here is X. So the shape is a bit different. So eventually they had the shape which is almost like harmonic oscillator, but not quite harmonic. And then if you perturb a little bit, the distribution changed a bit. It's obvious, yes? But with, in a sense, I'm joking, bad will. It was a good will, but bad will, they did these changes of potential in such a way that the probability distribution, so Tomasz, are you aware of this? That probability distribution was more or less like, this should go like, for instance, linearly, and then, so this will be Wigner. Wigner-Salmais. So P of S is like Wigner-Salmais, so here is S. So Wigner-Salmais is like this, P of S goes like S e2 minus S square. What it means? They found such a system, this is a potential, so Hamiltonian is trivial, is equal to P square over 2m plus V of X, which is here this one, here is V of X, and the spectrum was constructed in such a way, because potential was constructed in such a way, that the spectrum displayed Wigner distribution, which is typical for what? For quantum chaotic systems. And this is, of course, a regular system. It's one-dimensional potential. So you see, in a sense, I'm joking, bad will, but no. You see, you can construct such counterexamples, but they are of measure 0. Are you with me? I think it's a very nice example, but I forgot now the name of the first author who did it. You recall, Tomasz?
Is it the Boo's potential, if I'm not wrong, where the back construct?
So the potential is clear, it's just modified harmonic oscillator potential, modified in such a way to get levels change distribution to produce such a, on purpose, to produce such a Wigner-like distribution of P of S. So then it looks like a contradiction because you have a system with regular dynamics such that spacing distribution is Wigner-like, so looking at it you could guess that it is chaotic, but it's not. But thanks for the question. It's a good one, yeah?
But it has a well-defined semi-classical limit and all. Everything is fine in this case, right? Because conjecture, when they are mentioned, then one has to be sure that there is a well-defined semi-classical limit. So if you have such potential, is there a well-defined semi-classical limit?
Wow. I don't think so. So here was just, in a sense, a game to find such a system, in a sense, a kind of artificial system, specially designed such that it's regular and produces such P of S, yes? But just to show that this, with this conjecture, it is not like one-to-one. It's not a statement if-then. Thank you very much. Very good point. And of course, look, in the literature, this is one of examples which came to my mind, but there are many other examples like this.
But anything in many-body quantum chaotic systems, many-body systems where you can...
Wow, okay. Look, if this is for a single body, you can produce such a counterexample, apparent counterexample. If you have many bodies, then of course, in a sense, this Spielraum, so the play, how is it called in English? What is Spielraum? Playground is much larger. So of course you can, well, if you have, in a sense, good will of looking for counterexamples, you will find them, I presume. Larger playground, yes, thank you.
Okay, I think we can stop here. So let's thank Karol again.
Thank you very much. Thank you for being